Non-equilibrium thermodynamics is a branch of thermodynamics that deals with physical systems that are not in thermodynamic equilibrium but can be described in terms of variables, non-equilibrium state variables, that represent an extrapolation of the variables used to specify the system in thermodynamic equilibrium. Non-equilibrium thermodynamics is concerned with transport processes and with the rates of chemical reactions. It relies on what may be thought of as more or less nearness to thermodynamic equilibrium. Non-equilibrium thermodynamics is a work in progress, not an established edifice. This article will try to sketch some approaches to it and some concepts important for it. Almost all systems found in nature are not in thermodynamic equilibrium, for they are changing or can be triggered to change over time, and are continuously and discontinuously subject to flux of matter and energy to and from other systems and to chemical reactions. Some systems and processes are, however, in a useful sense, near enough to thermodynamic equilibrium to allow description with useful accuracy by currently known non-equilibrium thermodynamics. Nevertheless, many natural systems and processes will always remain far beyond the scope of non-equilibrium thermodynamic methods. This is because of the very small size of atoms, as compared with macroscopic systems. The thermodynamic study of non-equilibrium systems requires more general concepts than are dealt with by equilibrium thermodynamics. One fundamental difference between equilibrium thermodynamics and non-equilibrium thermodynamics lies in the behavior of inhomogeneous systems, which require for their study knowledge of rates of reaction which are not considered in equilibrium thermodynamics of homogeneous systems. This is discussed below. Another fundamental and very important difference is the difficulty or impossibility in defining entropy at an instant of time in macroscopic terms for systems not in thermodynamic equilibrium. Scope of non-equilibrium thermodynamics. Difference between equilibrium and non-equilibrium thermodynamics. A profound difference separates equilibrium from non-equilibrium thermodynamics. Equilibrium thermodynamics ignores the time courses of physical processes. In contrast, non-equilibrium thermodynamics attempts to describe their time courses in continuous detail. Equilibrium thermodynamics restricts its considerations to processes that have initial and final states of thermodynamic equilibrium. The time courses of processes are deliberately ignored. Consequently, equilibrium thermodynamics allows processes that pass through states far from thermodynamic equilibrium, that cannot be described even by the variables admitted for non-equilibrium thermodynamics, such as time rates of change of temperature and pressure. For example, in equilibrium thermodynamics, a process is allowed to include even a violent explosion that cannot be described by non-equilibrium thermodynamics. Equilibrium thermodynamics does, however, for theoretical development, use the idealized concept of the quasi-static process. A quasi-static process is a conceptual, timeless and physically impossible, smooth mathematical passage along a continuous path of states of thermodynamic equilibrium. It is an exercise in differential geometry rather than a process that could occur in actuality. Non-equilibrium thermodynamics, on the other hand, attempting to describe continuous time courses, need its state variables to have a very close connection with those of equilibrium thermodynamics. This profoundly restricts the scope of non-equilibrium thermodynamics, and places heavy demands on its conceptual framework. Non-equilibrium state variables. The suitable relationship that defines non-equilibrium thermodynamic state variables is as follows. On occasions when the system happens to be in states that are sufficiently close to thermodynamic equilibrium, non-equilibrium state variables are such that they can be measured locally with sufficient accuracy by the same techniques as are used to measure thermodynamic state variables, or by corresponding time and space derivatives, including fluxes of matter and energy. In general, non-equilibrium thermodynamic systems are spatially and temporally non-uniform, but their non-uniformity still has a sufficient degree of smoothness to support the existence of suitable time and space derivatives of non-equilibrium state variables. Because of the spatial non-uniformity, non-equilibrium state variables that correspond to extensive thermodynamic state variables have to be defined as spatial densities of the corresponding extensive equilibrium state variables. On occasions when the system is sufficiently close to thermodynamic equilibrium, intensive non-equilibrium state variables, for example temperature and pressure, correspond closely with equilibrium state variables. It is necessary that measuring probes be small enough, and rapidly enough responding, to capture relevant non-uniformity. Further, the non-equilibrium state variables are required to be mathematically functionally related to one another in ways that suitably resemble corresponding relations between equilibrium thermodynamic state variables. In reality, these requirements are very demanding, and it may be difficult or practically, or even theoretically, impossible to satisfy them. This is part of why non-equilibrium thermodynamics is a work in progress. Overview. Non-equilibrium thermodynamics is a work in progress, not an established edifice. This article will try to sketch some approaches to it and some concepts important for it. Some concepts of particular importance for non-equilibrium thermodynamics include time rate of dissipation of energy, Rayleigh 1873, Onsager 1931, also, time rate of entropy production, Onsager 1931, thermodynamic fields, dissipative structure, and nonlinear dynamical structure. One problem of interest is the thermodynamic study of non-equilibrium steady states, in which entropy production and some flows are non-zero, but there is no time variation of physical variables. One initial approach to non-equilibrium thermodynamics is sometimes called classical irreversible thermodynamics. There are other approaches to non-equilibrium thermodynamics, for example extended irreversible thermodynamics, and generalized thermodynamics, but they are hardly touched on in the present article. Quasi-radiationless non-equilibrium thermodynamics of matter in laboratory conditions. According to Wilt, see also Essex, current versions of non-equilibrium thermodynamics ignore radiant heat. They can do so because they refer to laboratory quantities of matter under laboratory conditions with temperatures well below those of stars. At laboratory temperatures, in laboratory quantities of matter, thermal radiation is weak and can be practically nearly ignored. But, for example, atmospheric physics is concerned with large amounts of matter, occupying cubic kilometers, that, taken as a whole, are not within the range of laboratory quantities, then thermal radiation cannot be ignored. Local equilibrium thermodynamics. The terms classical irreversible thermodynamics and local equilibrium thermodynamics are sometimes used to refer to a version of non-equilibrium thermodynamics that demands certain simplifying assumptions, as follows. The assumptions have the effect of making each very small volume element of the system effectively homogeneous, or well mixed, or without an effective spatial structure, and without kinetic energy of bulk flow or of diffusive flux. Even within the thought frame of classical irreversible thermodynamics, care is needed in choosing the independent variables for systems. In some writings, it is assumed that the intensive variables of equilibrium thermodynamics are sufficient as the independent variables for the task. Such variables are considered to have no memory, and do not show hysteresis. In particular, local flow intensive variables are not admitted as independent variables. Local flows are considered as dependent on quasi-static local intensive variables. Also, it is assumed that the local entropy density is the same function of the other local intensive variables as in equilibrium. This is called the local thermodynamic equilibrium assumption. See also Kaiser, 1987. Radiation is ignored because it is transfer of energy between regions, which can be remote from one another. In the classical irreversible thermodynamic approach, there is allowed very small spatial variation, from very small volume element to adjacent very small volume element, but it is assumed that the global entropy of the system can be found by simple spatial integration of the local entropy density. This means that spatial structure cannot contribute as it properly should to the global entropy assessment for the system. This approach assumes spatial and temporal continuity and even differentiability of locally defined intensive variables such as temperature and internal energy density. All of these are very stringent demands. Consequently, this approach can deal with only a very limited range of phenomena. This approach is nevertheless valuable because it can deal well with some macroscopically observable phenomena. In other writings, local flow variables are considered. These might be considered as classical by analogy with the time-invariant long-term time averages of flows produced by endlessly repeated cyclic processes. Examples with flows are in the thermoelectric phenomena known as the Seebeck and the Peltier effects, considered by Kelvin in the 19th century and by Onsager in the 20th. These effects occur at metal junctions, which were originally effectively treated as two-dimensional surfaces, with no spatial volume, and no spatial variation. Local equilibrium thermodynamics with materials with memory. A further extension of local equilibrium thermodynamics is to allow that materials may have memory, so that their constitutive equations depend not only on present values but also on past values of local equilibrium variables. Thus time comes into the picture more deeply than for time-dependent local equilibrium thermodynamics with memoryless materials, but fluxes are not independent variables of state. Extended irreversible thermodynamics. Extended irreversible thermodynamics is a branch of non-equilibrium thermodynamics that goes outside the restriction to the local equilibrium hypothesis. The space of state variables is enlarged by including the fluxes of mass, momentum, and energy and eventually higher-order fluxes. The formalism is well suited for describing high-frequency processes and small-length scales materials. Basic concepts. There are many examples of stationary non-equilibrium systems, some very simple, like a system confined between two thermostats at different temperatures or the ordinary coat flow, a fluid enclosed between two flat walls moving in opposite directions and defining non-equilibrium conditions at the walls. Laser action is also a non-equilibrium process, but it depends on departure from local thermodynamic equilibrium and is thus beyond the scope of classical irreversible thermodynamics. Here a strong temperature difference is maintained between two molecular degrees of freedom, with molecular laser, vibrational and rotational molecular motion, the requirement for two component temperatures in the one small region of space, precluding local thermodynamic equilibrium, which demands that only one temperature be needed. Damping of acoustic perturbations or shock waves are non-stationary non-equilibrium processes. Driven complex fluids, turbulent systems, and glasses are other examples of non-equilibrium systems. The mechanics of macroscopic systems depends on a number of extensive quantities. It should be stressed that all systems are permanently interacting with their surroundings, thereby causing unavoidable fluctuations of extensive quantities. Equilibrium conditions of thermodynamic systems are related to the maximum property of the entropy. If the only extensive quantity that is allowed to fluctuate is the internal energy, all the other ones being kept strictly constant, the temperature of the system is measurable and meaningful. The system's properties are then most conveniently described using the thermodynamic potential Helmholtz free energy, A equals U, Ts, a Legendre transformation of the energy. If, next to fluctuations of the energy, the macroscopic dimensions, volume, of the system are left fluctuating, we use the Gibbs free energy, G equals U plus PV, Ts, where the system's properties are determined both by the temperature and by the pressure. Stationary states, fluctuations, and stability. In thermodynamics one is often interested in a stationary state of a process, allowing that the stationary state include the occurrence of unpredictable and experimentally unreproducible fluctuations in the state of the system. The fluctuations are due to the system's internal sub-processes and to exchange of matter or energy with the system's surroundings that create the constraints that define the process. If the stationary state of the process is stable, then the unreproducible fluctuations involve local transient decreases of entropy. The reproducible response of the system is then to increase the entropy back to its maximum by irreversible processes. The fluctuation cannot be reproduced with a significant level of probability. Fluctuations about stable stationary states are extremely small except near critical points. Kohn Deputy and Prigozhin 1998, page 323. The stable stationary state has a local maximum of entropy and is locally the most reproducible state of the system. There are theorems about the irreversible dissipation of fluctuations. Here local means local with respect to the abstract space of thermodynamic coordinates of state of the system. If the stationary state is unstable, then any fluctuation will almost surely trigger the virtually explosive departure of the system from the unstable stationary state. This can be accompanied by increased export of entropy. Local thermodynamic equilibrium. The scope of present-day non-equilibrium thermodynamics does not cover all physical processes. A condition for the validity of many studies in non-equilibrium thermodynamics of matter is that they deal with what is known as local thermodynamic equilibrium. Local thermodynamic equilibrium of ponderable matter. Local thermodynamic equilibrium of matter, see also Kaiser, 1987, means that conceptually, for study and analysis, the system can be spatially and temporally divided into cells or microphases of small, infinitesimal, size, in which classical thermodynamical equilibrium conditions for matter are fulfilled to good approximation. These conditions are unfulfilled, for example, in very rarefied gases, in which molecular collisions are infrequent, and in the boundary layers of a star, where radiation is passing energy to space, and for interacting fermions at very low temperature, where dissipative processes become ineffective. When these cells are defined, one admits that matter and energy may pass freely between contiguous cells, slowly enough to leave the cells in their respective individual local thermodynamic equilibria with respect to intensive variables. One can think here of two relaxation times separated by order of magnitude. The longer relaxation time is of the order of magnitude of times taken for the macroscopic dynamical structure of the system to change. The shorter is of the order of magnitude of times taken for a single cell to reach local thermodynamic equilibrium. If these two relaxation times are not well separated, then the classical non-equilibrium thermodynamical concept of local thermodynamic equilibrium loses its meaning and other approaches have to be proposed. See for instance extended irreversible thermodynamics. For example, in the atmosphere, the speed of sound is much greater than the wind speed. This favors the idea of local thermodynamic equilibrium of matter for atmospheric heat transfer studies at altitudes below about 60 km where sound propagates, but not above 100 km, where, because of the paucity of intermolecular collisions, sound does not propagate. Milnes 1928 definition of local thermodynamic equilibrium in terms of radiative equilibrium. Milne, 1928, Thinking About Stars, gave a definition of local thermodynamic equilibrium in terms of the thermal radiation of the matter in each small local cell. He defined local thermodynamic equilibrium in a cell by requiring that it macroscopically absorb and spontaneously emit radiation as if it were in radiative equilibrium in a cavity at the temperature of the matter of the cell. Then it strictly obeys Kirchhoff's law of equality of radiative emissivity and absorptivity, with the black body source function. The key to local thermodynamic equilibrium here is that the rate of collisions of ponderable matter particles such as molecules should far exceed the rates of creation and annihilation of photons. Entropy in evolving systems. It is pointed out by W.T. Grandi Jr. that entropy, though it may be defined for a non-equilibrium system, is when strictly considered, only a macroscopic quantity that refers to the whole system, and is not a dynamical variable and in general does not act as a local potential that describes local physical forces. Under special circumstances, however, one can metaphorically think as if the thermal variables behaved like local physical forces. The approximation that constitutes classical irreversible thermodynamics is built on this metaphoric thinking. This point of view shares many points in common with the concept and the use of entropy in continuum thermomechanics, which evolved completely independently of statistical mechanics and maximum entropy principles. Speculated extremal principles for non-equilibrium processes. Until recently, prospects for useful extremal principles in this area have seemed clouded. Sini-Coles, 1999, concludes that one model of atmospheric dynamics has an attractor which is not a regime of maximum or minimum dissipation. She says this seems to rule out the existence of a global organizing principle, and comments that this is to some extent disappointing. She also points to the difficulty of finding a thermodynamically consistent form of entropy production. Another top expert offers an extensive discussion of the possibilities for principles of extrema of entropy production and of dissipation of energy. Chapter 12 of Grandi, 2008, is very cautious, and finds difficulty in defining the rate of internal entropy production in many cases, and finds that sometimes for the prediction of the course of a process, an extremum of the quantity called the rate of dissipation of energy may be more useful than that of the rate of entropy production. This quantity appeared in Onsager's 1931 origination of this subject. Other writers have also felt that prospects for general global extremal principles are clouded. Such writers include Glanzdorf and Prigozhin, 1971, Leben, Ju and Casas Vasquez, 2008, and Ilhav, 1997. A recent proposal may perhaps bypass those clouded prospects. Applications of non-equilibrium thermodynamics. Non-equilibrium thermodynamics has been successfully applied to describe biological processes such as protein folding/unfolding and transport through membranes. Also, ideas from non-equilibrium thermodynamics and the informatic theory of entropy have been adapted to describe general economic systems.
Please subscribe and thanks for watching.